Hi, Professor and everyone. We are Group 12, and the following are our group's members. And this is our outline. The first part will be our motivation. Recently, Windows 11 was launched, and the loading icon is plenty of dots spinning as a circle. Surprisingly, we came up with the idea that it's something that has period, and we want to design the device that calculates time by this kind of idea. Then we are going to talk about our introduction. We designed a construction drawing as the left figure. We will put the ball into the U-shaped track, and it will swing in it. Because of the friction, which is the biggest obstacle in realization, we choose to use an accelerator to keep it swinging. And the right figure is our realization device. We will discuss all the details in the following presentation. Next, we are going to analyze the items in this page. There are two parts. One is the different slope curves, and another is the accelerator. The first thing we need to do is to find out the relationship between time and position of ball. We do the second derivative on the acceleration to obtain the position. Then, by fundamental theorem of calculus, we can obtain an ODE of the position and slope function. Then, we take the slope function as linear and quadratic function. The linear case is easy to analyze. However, the quadratic case becomes a nonlinear ODE, which is out of our knowledge bound.
And then, for the next case, we consider the Brachistochrone curve. Fermat's principle states that the path taken by a ray between two given points is the path that can be traveled in the least time. We can use this principle to derive the Brachistochrone curve by considering the trajectory of a beam of light, with the speed of light increases following a constant vertical acceleration. By the conservation of energy, the instantaneous speed v of a ball is square root of 2gy, where y is the falling height. Note that the speed of motion of a ball along an arbitrary curve does not depend on the horizontal displacement. By the law of reflection, we have this equation, where Vm is the constant and theta represents the angle of the trajectory with respect to the vertical. The equation above leads to two conclusions. The first is, at the one set, the angle must be zero when the particle speed is zero. And the second is, the speed reaches a maximum value when the trajectory becomes horizontal. That is when the angle theta equals to 90 degrees. Now, let's assume that the particle reaches maximum speed at the point xy after falling vertical distance d. So the Vm will equal to square root of 2gd. After rearranging terms in the law of reflection and square root give us this equation, which can be solved for dx in terms of dy into the second equation. And the differential equation of an inverted cycloid generated by a circle of diameter is that.
The above analyses are only about the slope and time. Next, we consider the accelerator. The reason that we use the accelerator is that the ball will stop by the friction. We must force the ball keep swinging. Let's play a video of our device without accelerator. We can see that the ball stops in a really fast rate. However, there is a question. Could a device with accelerator calculate time? Would it be we have tried some analysis on this question. If the accelerator provides a constant energy to the ball, and the energy loss of the ball falls from height h, is a function e of h, we could write down the function by energy and consider the height of each swing as an infinite sequence. Then, by the total energy, we could write down an iterative equation that calculates the height hi by hi minus 1. Since the space we consider is the real number space, we try to prove that the iterative function is a gamma contraction mapping. As a result, we thought that we can always find a constant gamma that less than 1, which satisfies the condition. Last, by Banach fixed point theorem, we know that the gamma contraction mapping will always converge to a unique point. Although it's not a rigorous proof, we also have written a program to test several feasible slope and energy. The height and time actually converge. Therefore, we believe it can accurately calculate time like a timer. And later on, we will present the experiment results that prove our device works.
Okay, it's time to our simulation. To simulate the experiment, I use Python to visualize the full process. Also, in the simulation, we assume that there is no friction when the ball is rolling. And to simulate the ball's movement, I calculate each state in an iterative way. Now, let's see how to simulate the ball's movement in Brooksistron. Okay. To calculate the ball's movement in Brooksistron, we first need to calculate the polar coordinate theta using the ball's current position and the formula that derived from the definition of Brooksistron, which is theta equal to x over r plus square root of y times 2r minus y over r. And after we have theta, we can calculate the slope of tangent line from the formula. Okay, so dy over dx equal to cotangent theta over 2. After that, we need to calculate the change of energy. And in our assumption, there is no friction, and we can calculate the difference of energy by using the height difference from current position and out position. The formula is like the following: E prime equal to H prime minus H over NG. Okay, so also because of our assumption, the energy difference is fully transferred into kinetic energy, and we can acquire new velocity from the kinetic energy using the formula V equal to square root of 2E over N. Okay. So when we have a new velocity and we also have dt, so we can calculate the small movement and split the movement into x direction and y direction, and apply those movement, and we can have our next iteration to calculate the next movement. So do it repeatedly, and we can have our gift picture playing, and it's clear show that there is some period in low slope. Okay, thank you.
To realize our idea, we have designed a track made with transparent plastic pipes to let an iron ball roll inside it. The pipe is fixed on a vertical wood board with plastic holders, and the pipe is bended with the shape of a cycloid. On account of the friction and the resistance in real world, to balance the energy loss, we need an accelerator to keep iron ball rolling.
Then I will introduce the accelerator. As shown in the picture on the left, the first thing that can be thought of is that when the sensor detects the iron ball, the coil is energized to accelerate the iron ball. However, when the power is turned on and in appropriate time, the iron ball will accelerate in the wrong direction. When one of the sensors detects the ball, we must energize the coil to accelerate the ball. But in this case, it won't be triggered when another sensor detects it, because of the properties of the ball, which means that I only need to trigger the coil at even number of times. We use infrared transmitter and receiver with OP as a threshold as a sensor. Through the OR gate signal and the feature of the T flip-flop, the signal is transformed into the waveform shown on the right. It then connects a MOSFET through the output as a switch to control the coil. Since the store didn't steal T flip-flop IC, JK were used instead. We connect the JK of the JK port flip-flop. And it was found that the acceleration time after the trigger was not enough. So we connect the output to the one-shot mode of the NE555 to extend the acceleration time and also control it. In the end, we found that 5 volt was not enough to drive the electron magnet. So we add an additional 24-volt voltage source to drive it. Then we look at the simulation of the entity. The two LEDs on the left represent the Q and Q bar of our T flip-flop. And the LED on the right is an indicator that shows if we want to trigger the accelerator. We can see the state of the iron ball running in the track, and we will find that the swing of the iron ball is sometimes reduced, and then pushed up again, which proves that our accelerator is working and it actually will converge. Thus, it is a device to calculate the time well.
After we build the device, we have conducted some experiments on it. We count the period of our device. 10 periods cost about 13.1 seconds. We conduct the experiment for 70 periods and calculate how much time passed 10 periods each. We also conduct the experiment for 240 periods and calculate the time passed 2 periods each. Here is the result for 70 consecutive periods. For the first 10 periods, it takes 12.98 seconds. For the second 10 periods, it takes 13.17 seconds. For the third 10 periods, it takes 13.12 seconds. And for the rest of our results, they take 12.92, 13.02, 13.14, 13.88 seconds, respectively. This is our line chart of the time passed after X periods. As you can see, it is a straight line. And this is the experiment for 240 periods. The green line is the mean value of the periods, and the dark green area is 1 standard deviation, and the light green area is 2 standard deviation. The variance of the experiment is 0.004. In conclusion, we have overcome the resistance and friction in the real world with the accelerator. Also, we create a device with stable periods. Moreover, the device can continue running for hours. To sum up, our device is exactly a successful timer. Thanks for listening.